Tonight, we're going to examine what physics actually says about the boundary defined by the speed of light, what lies on the far side of it, and whether the boundary is truly as absolute as it appears. This is a question that sits at the intersection of the most precisely tested physical theory ever constructed and some of the deepest open problems in fundamental science, and the honest answer to it is considerably more nuanced than either the popular dismissal that nothing can exceed light speed or the popular fantasy that someone will eventually figure out a workaround. The speed of light in vacuum, approximately 299,792,458 meters per second, is not a speed record that some future technology will beat the way aircraft broke the sound barrier. The analogy between those two barriers is one of the most misleading in all of popular science, because the sound barrier was an engineering challenge, a cluster of aerodynamic difficulties that made supersonic flight hard rather than a structural feature of nature that made it impossible. The light barrier is genuinely different. It is a property of spacetime itself, a built-in feature of the four-dimensional structure of the universe, and attempting to exceed it with a physical object or an information-carrying signal runs into mathematical impossibilities that no amount of engineering ingenuity can circumvent, at least not within the framework that current physics describes. And yet the question of what lies beyond it is not idle. The universe already contains, in multiple specific and carefully confirmed ways, phenomena that exceed the speed of light. Not by accident, not through loopholes in the physics, but as genuine features of the standard picture that the same physics predicts and verifies. Distant galaxies are receding from us faster than light right now, not because they are moving through space at superluminal speeds, but because the space between us and them is expanding. During the universe's inflationary epoch, the rapid expansion of space exceeded the speed of light by factors that make any human-engineered speed seem laughably small. The phase velocities of electromagnetic waves in certain materials exceed c in ways that are real and measurable. Geometric points, the intersections of things rather than things themselves, can move at any speed whatsoever. Distinguishing which of these faster-than-light phenomena are genuine departures from the standard picture, which are features of the standard picture itself, and which cannot be used to send information or transport matter regardless of what they do, is the primary intellectual task of tonight's investigation. That task turns out to be one of the most productive exercises in precision thinking that the physical sciences offer, because getting the distinctions right requires understanding not just what the speed of light is, but what kind of thing the speed limit is, why the universe enforces it the specific way it does, and where the genuine edges of our knowledge sit. By the end of tonight, you will understand the exact nature of the light barrier, the multiple distinct ways the universe already exceeds it, the most serious physics-based proposals for genuine faster-than-light travel or communication, and why they face fundamental rather than merely engineering obstacles, the deep connections between the speed of light and causality in information, and the specific places where current physics might be incomplete enough that the picture could change. If this kind of thorough, careful, honest investigation of the universe's most fascinating and consequential speed limit is what you are here for, subscribe and leave a like. It helps this channel reach people who want the complete and honest version rather than the simplified one. Now let us start at the foundation with a precise statement of what the speed of light actually is. This investigation is also timely in a way that goes beyond the timeless philosophical appeal of the question. The last decade has seen the first direct detection of gravitational waves, providing the most precise confirmation yet that gravitational influences travel at sea. It has seen the development of increasingly sensitive tests of Lorentz invariance that push the precision of our knowledge of the speed limit to levels unimaginable a generation ago. It has seen the James Webb Space Telescope reveal galaxies in the universe's first few 100 million years, galaxies that are now receding from us at many times the speed of light but whose ancient light has reached us after billions of years in transit through expanding space. And it has seen theoretical advances in quantum gravity that have sharpened our understanding of what the speed limit means at the Planck scale. The question of what lies beyond a light barrier is therefore not a settled question dressed up as an open one for dramatic effect. It is a genuinely open question in specific, well-defined senses, open about whether current physics is complete at the Planck scale, open about whether the universe contains structures beyond the cosmic event horizon that differ from what we observe inside it, and open about whether any future theory of quantum gravity will preserve the speed limit precisely or reveal corrections that current experiments cannot detect. The most important thing to understand about the speed of light is that it is not primarily a property of light. Light happens to travel at a certain speed because light is a massless excitation of the electromagnetic field, and massless excitations of any field naturally propagate at the universe's maximum speed. But the maximum speed, the quantity we call c, exists independently of light and would exist even if light did not. It is the conversion factor between space and time in the four-dimensional geometry of spacetime, the parameter that tells you how much one dimension can be traded for the other. This framing matters enormously for understanding the light barrier. If c were merely the speed light happens to travel, you might reasonably ask whether some future technology could carry things faster, just as future technology carried aircraft faster than sound despite sound having its own specific propagation speed. But c is not the speed that light happens to have. It is the maximum speed that any causal influence can travel in the spacetime geometry described by special relativity, and light achieves this maximum precisely because it has no rest mass to prevent it from doing so. Einstein's 1905 paper that introduced special relativity rested on two postulates, one of which was that the speed of light in vacuum is the same for all inertial observers regardless of their relative motion. This postulate was not chosen arbitrarily. It was the conclusion forced on Einstein by James Clerk Maxwell's equations of electromagnetism, published in 1865. Those equations describe how electric and magnetic fields evolve in time, and they predict that electromagnetic disturbances propagate through vacuum at a specific speed, 1 divided by the square root of the product of the electric permittivity and magnetic permeability of free space. The numerical value of this expression matched the measured speed of light precisely, establishing that light is an electromagnetic phenomenon and that its speed is set by the electromagnetic constants of the vacuum. The problem that motivated Einstein was that Maxwell's equations give a specific speed for light without specifying speed relative to what. In Newtonian mechanics, speeds add simply. A ball thrown forward at 10 meters per second from a train moving at 30 meters per second moves at 40 meters per second relative to someone standing still on the ground. If this simple addition applied to light, then observers in different states of motion should measure different speeds for the same light beam. But the Michelson-Morley experiment of 1887 found no variation in light speed despite Earth's considerable orbital velocity around the Sun. Einstein's resolution was to take seriously that light travels at c for all observers, and to work out what this requires about the nature of space and time. What it requires is that space and time are not independent quantities. Moving observers measure different lengths and different time intervals for the same events, and they disagree about what events are simultaneous. The specific relationship between their measurements is given by the Lorentz transformation, which contains c as the conversion factor between space and time. In natural units where c equals 1, space and time have the same units, and the symmetry between them is manifest. The speed c is not a speed in the everyday sense of a distance divided by time measured in separate meters and seconds. It is the exchange rate between space and time as aspects of a unified four-dimensional geometry. In the meter definition used since 1983, 1 meter is defined as the distance light travels in exactly 1/299,792,458 of a second. This makes c exactly equal to 299,792,458 meters per second by definition, and distance is operationally defined by light travel time. The precision of this definition reflects how deeply c is embedded in the operational foundations of measurement. The question of whether c has changed over cosmic time is in this framework the question of whether the conversion rate between the spatial and temporal dimensions of space-time has changed, which would have far-reaching consequences for the entire physical description of the universe. The constancy of c across all physical processes is one of the most thoroughly tested facts in science, not merely in electromagnetism, where it was first established, but in gravitational wave physics, in atomic clocks, in the behavior of high-energy particles, in astrophysical observations of distant objects. C appears everywhere with the same value. The fact that it enters into so many apparently different contexts From the relationship between electric and magnetic fields to the energy of nuclear reactions to the rate at which gravitational information propagates to the relationship between mass and energy, reflects its nature as a property of spacetime itself rather than a property of any particular force or particle. The question of whether c was the same in the early universe as it is today is an active research area. Some speculative theoretical frameworks, called varying speed of light theories, propose that c was different in the early universe and has changed over cosmic time. These theories are motivated partly by the desire to solve the horizon problem that inflation was designed to address, by a different mechanism. However, the observational constraints on any variation in c over cosmic time are extremely tight, coming from measurements of fine structure constant variations in quasar absorption spectra and from Big Bang nucleosynthesis calculations, which are sensitive to the early universe values of the fundamental constants. Current observations are consistent with c being constant to high precision over the age of the universe. Special relativity specifies precisely what happens to the energy and momentum of a moving object as its velocity approaches the speed of light, and the picture that emerges is unambiguous. Reaching c requires an infinite amount of energy for any object with non-zero rest mass. This is not a practical engineering difficulty like the enormous cost of building a very fast rocket. It is a mathematical divergence, a quantity that grows without bound, requiring literally infinite energy to achieve the limiting value. The relativistic energy of a particle with rest mass m moving at velocity v is given by gamma times mc squared, where gamma is the Lorentz factor, 1 divided by the square root of 1 minus v squared over c squared. At low velocities, gamma is approximately 1, and the energy is approximately mc squared plus 1/2 mv squared, the rest energy plus the familiar classical kinetic energy. As v approaches c, the denominator of gamma approaches 0, making gamma and therefore the total energy diverge without limit. There is no finite value of v at which the energy becomes infinite. The divergence occurs exactly at v equals c and only there. The Large Hadron Collider at CERN illustrates this effect at the practical scale of modern engineering. The LHC accelerates protons to approximately 99.9999991% of the speed of light. At this velocity, the Lorentz factor is roughly 7,460, meaning the proton's total energy is about 7,460 times its rest mass energy. Each proton in the LHC at full energy has a kinetic energy of about 6.5 teri-electronvolts, which sounds impressive but corresponds to roughly the kinetic energy of a flying mosquito concentrated into a single subatomic particle. Getting from 99.9999991% of C to 99.9999999% would require another enormous injection of energy and would yield only a tiny fractional increase in actual velocity. The energy invested returns ever-diminishing increments of speed. The momentum perspective gives the same conclusion through a different route. Relativistic momentum is gamma times mv. As v approaches c, gamma diverges and momentum diverges with it. Since force equals rate of change of momentum, and finite forces applied over finite times can only deliver finite impulse, no finite force applied for any finite duration can push a massive particle to c. The accumulated impulse required to reach c is infinite. The reason this is a fundamental mathematical barrier, rather than a practical one, is worth emphasizing. Some physical arguments suggest barriers that are in principle overcomable by new physics. The light-speed barrier is not of this kind. It follows mathematically from the Lorentz transformation, which is the fundamental relationship between space and time measurements in special relativity. Any theory that preserves the Lorentz transformation preserves the light-speed barrier. A theory that modifies the Lorentz transformation at high energies could in principle modify the barrier, but every high-energy experiment conducted to date has found Lorentz invariance preserved with extraordinary precision, and the constraints from astrophysical observations are even tighter. The Lorentz factor behavior also explains why particle accelerators can never fully achieve their goal of reaching arbitrarily high collision energies by simply making the accelerating field stronger or longer. Each doubling of energy beyond relativistic threshold buys ever smaller increments of velocity. The LHC's proton energy is more than 7,000 times the proton rest mass energy, yet the proton's velocity is still measurably less than c. To double the proton's velocity from 99.9999991% to 99.9999995% of c would require nearly doubling the LHC's already enormous stored beam energy. This practical demonstration of the energy wall is one of the most concrete pieces of evidence that special relativity is not just theoretically correct but operationally necessary. Every engineering decision in accelerator design depends on the relativistic energy-momentum relationship being exactly right. If the relationship were only approximately correct, the beams would follow incorrect trajectories in the magnets, the timing of radio frequency cavities would be wrong, and the detectors would give incorrect results. The fact that the LHC works as designed, that beams circulate for hours at the predicted energies, and the detectors see the predicted particle rates, is a continuous real-time test of special relativity at some of the most extreme conditions human technology has achieved. A useful way to appreciate the energy wall is to note that the kinetic energy of an LHC proton, roughly 6.5 tera-electronvolts, is roughly equivalent to the kinetic energy of a mosquito in flight, about 1 microjoule. But this is concentrated into a single particle a billion times smaller than a cell. The energy density is extraordinary, and the fact that it still cannot push the proton to c is the energy wall made concrete. The approach to the speed of light involves systematic and coordinated changes in the way an object experiences time and in the way its dimensions are measured. These changes, time dilation and length contraction, are not separate phenomena layered on top of Newtonian mechanics. They are aspects of a single geometric reality, the rotation of the object's coordinate system in four-dimensional spacetime as its The existence of a finite maximum speed in the laws of physics is not self-evident, and understanding why the universe has one requires thinking about what the alternatives would imply. A universe with no maximum speed, or with an infinite maximum speed, would have a fundamentally different causal structure from the one we observe, and the specific difficulties that arise in such a universe illuminate why the light barrier is not an arbitrary restriction but a structural necessity for a coherent physical description. In Newtonian mechanics, there is no maximum speed. Gravitational influences act instantaneously across any distance. In principle, you could exert a force on an object at the far end of the universe, and it would respond immediately with information about the application of the force traveling there instantaneously. Newton was aware of the philosophical difficulty this posed. He described gravitational action at a distance as absurd and explicitly acknowledged that he had no satisfactory physical explanation for it. Despite the absurdity, the theory worked extraordinarily well within the domain of experience available to Newton and his contemporaries, because the speeds involved were always so much slower than c that relativistic effects were undetectable. The problem with infinite propagation speed becomes most acute when combined with the principle that physics should look the same in all inertial reference frames. If there is no maximum speed, then observers moving at different velocities should still agree on which events are simultaneous. But this turns out to require an absolute notion of time, a universal clock that runs at the same rate everywhere, which is precisely what Newton assumed. The Michelson-Morley experiment and subsequent measurements showed that this assumption was wrong. The constancy of the speed of light for all observers is incompatible with absolute simultaneity. A finite maximum speed removes the need for absolute simultaneity. Instead, what is universal is the causal structure of spacetime, whether two events are related as cause and effect, or whether they are space-like separated and therefore unable to influence each other, is the same in all reference frames. Causality, the principle that effects do not precede their causes, is enforced globally and consistently by the finite maximum speed. Without it, different observers would disagree about the causal ordering of events, making it impossible to have a consistent physical description that all observers could agree on. The specific value of c sets the scale of the trade-offs between space and time in the Lorentz transformation. A smaller c would mean that relativistic effects become significant at lower speeds, making everyday human experience more relativistic. A larger c would mean that relativistic effects become significant only at higher speeds, making the Newtonian approximation valid across a wider range. But as long as c is finite, the qualitative picture, the impossibility of infinite speed signals, the relativity of simultaneity, the existence of light cones separating causal from non-causal relationships all remain. The universe's choice of a specific value for c is an empirical fact. The existence of some finite maximum speed appears to be a theoretical necessity for a consistent relativistic causal structure. A universe with an infinite propagation speed faces a specific mathematical problem that becomes apparent when you try to write down relativistic laws of physics. In such a universe, forces would need to be modeled as acting instantaneously at a distance, meaning the force at a given location at a given time would depend on the positions and states of all other matter in the universe at the same instant. But defining what the same instant means requires a preferred notion of simultaneity, and the equivalence of all inertial frames means there can be no such preferred notion. The theoretical edifice of relativistic physics would be inconsistent. Finite propagation speeds are what make field theories possible. In field theories, the force between two objects is not transmitted instantaneously from one to the other, but is mediated by a field that propagates continuously through space. The electromagnetic field carries information about the charge distribution that produced it, but only at the speed of light. The gravitational field in general relativity propagates at c through space-time curvature. In quantum field theory, forces are mediated by gauge bosons that travel, at most at c. The entire framework of modern fundamental physics is built on local field theories with finite propagation speed, and c is the propagation speed of massless excitations of all known fields. This universality of c, its appearance as the propagation speed of every fundamental field in nature, strongly suggests that it is not a property of any particular field but of the spacetime in which all fields are embedded. If different fields propagated at different speeds, the spacetime structure would need to be more complicated, with different light cones for different fields, and the elegant geometry of Minkowski spacetime would be replaced by something more complex and arguably less physically motivated. The universe already contains an impressive collection of phenomena that travel faster than light or that exceed c in some precisely defined sense, and all of them are entirely consistent with special relativity. Understanding why they are consistent and what specifically they lack that prevents them from being used to send information faster than light is one of the most illuminating exercises in understanding what the speed limit actually prohibits. The most obvious examples involve geometric features rather than physical objects. Consider a laser beam sweeping across a distant surface. A laser on Earth pointing at the moon, rotating at a moderate angular velocity, creates a spot on the lunar surface that moves much faster than c. The moon is about 1.28 light seconds away. A laser rotating at 1 revolution per second would produce a spot moving at about twice pi times 384,400 kilometers per second, nearly 8,000 times the speed of light around the moon's surface. The spot is not a physical object. It is the intersection of a beam with a surface, a geometric feature, and geometric features are not subject to the speed limit because they carry no mass, no energy, and no information from one location to another. The speed of a geometric point is not a speed in the sense restricted by special relativity. The cosmic expansion provides a more dramatic example. According to Hubble's law, the recession velocity of a distant galaxy from the observer is proportional to its distance. The constant of proportionality, the Hubble constant, is approximately 70 kilometers per second per megaparsec. At a distance of roughly 14.4 billion light-years, the recession velocity equals c. Beyond that distance, galaxies are receding faster than c. This is not a violation of special relativity because the galaxies are not moving through space at those speeds. The space between the observer and the galaxy is expanding, and the recession velocity is the rate of change of the physical distance between them due to this expansion. Local velocities, measured relative to local inertial frames, remain below c everywhere. The scissors effect offers another geometric illustration. If two enormously long blades of a pair of scissors close at a moderate rate, the point where the two blades intersect move along the blades. For sufficiently long blades closing at a sufficiently shallow angle, this intersection point can move faster than c along the blades. No physical object moves at this speed. The intersection is a point where two surfaces happen to meet, not a thing traveling from one end of the scissors to the other. Nothing is transmitted along the blades faster than the mechanical stress waves that close them, which travel at the speed of sound in the blade material, nowhere near c. What all of these faster-than-light phenomena have in common is that they cannot be used to transmit information from one location to another faster than light. The moving laser spot cannot send a message from one end of the moon's surface to the other faster than a light beam could travel that distance directly. The intersection of scissors cannot carry a signal from one end of the blades to the other faster than any wave propagating through the blade material. The recession of distant galaxies cannot be used to communicate between them faster than a photon could travel through the expanding space between them. The quantum vacuum itself provides an interesting case. The vacuum is not empty in quantum field theory. It is a sea of fluctuating fields, with virtual particle-antiparticle pairs constantly appearing and annihilating. These fluctuations are not merely mathematical artifacts but have physical consequences, including the Casimir force between closely spaced conductors and corrections to the energy levels of hydrogen, called the Lamb shift. The question of whether information can propagate through vacuum fluctuations faster than light has been studied carefully, and the answer is no. Vacuum fluctuations are random and cannot carry a controlled signal. The quantum Zeno effect provides another apparent loophole that closes on examination. Repeated measurements of an unstable quantum system can slow or prevent its decay, because each measurement collapses the wave function back to the undecayed state. A very rapid sequence of measurements can effectively freeze the evolution of a quantum system. This seems potentially useful for faster-than-light manipulation, If you could use the Zeno effect at one location to instantaneously affect the quantum state at another location through entanglement, you might communicate faster than light. But the no communication theorem closes this loophole rigorously. The Zeno measurements at one location produced no detectable effect at the other location without a classical channel to compare results. The connection between the loophole zoo and the no communication theorem is instructive. Every apparent loophole in the speed limit that does not actually allow information transfer turns out to be disqualified by the same fundamental reason: the quantum randomness of measurement outcomes. You cannot control what result a quantum measurement gives, and without control over the results, you cannot encode a message. The randomness that makes quantum mechanics seem so philosophically strange is the same property that enforces the light speed limit at the quantum level. The speed of light in vacuum is c, but light in any material medium travels at a speed reduced by a factor called the refractive index of the medium. In water, the refractive index at visible wavelengths is approximately 1.33, meaning light travels through water at about 75% of c. In glass, depending on composition and wavelength, the refractive index ranges from about 1.5 to 1.9, giving speeds of 53 to 67% of c. Even air has a refractive index slightly above 1, making light in air fractionally slower than in vacuum. This reduced speed of light in materials creates a distinctive situation. Charged particles accelerated to relativistic velocities can move through these materials faster than light moves through the same material. The particle is not exceeding c, the universal speed limit. It is exceeding only the local speed of light in the medium. The universal speed limit is still c in vacuum, and the particle's speed in any vacuum environment is still less than c. But within the material, the particle outruns the electromagnetic disturbances it creates. When this happens, something remarkable occurs. The electromagnetic disturbances that the charged particle creates as it moves cannot propagate ahead of it in the medium. They pile up constructively behind the particle in a cone-shaped wavefront, similar in geometry to the sonic boom produced by an aircraft exceeding the speed of sound in air. This constructive interference produces coherent emission of light, concentrated in the cone, which is what Pavel Cherenkov first observed experimentally in 1934, and for which he shared the Nobel Prize in Physics in 1958 along with Igor Tamm and Ilya Frank, who provided the theoretical explanation. The half-angle of the Cherenkov cone is the arc cosine of the ratio of the speed of light in the medium to the particle's speed. For a particle just barely exceeding the medium's light speed, the angle is nearly zero, and the radiation is emitted nearly forward. For particles moving much faster than the medium's light speed, the angle is larger. Measuring the Cherenkov angle with precision gives a direct determination of the particle's velocity, which is a remarkably powerful technique for particle identification in high-energy physics experiments. Cherenkov radiation from fast-charged particles in water produces the characteristic blue glow visible in nuclear reactor cooling pools, where beta decay products travel at speeds exceeding the speed of light in water. The specific blue color reflects the spectrum of Cherenkov emission, which falls off toward longer wavelengths, concentrating the visible emission in the blue and ultraviolet region. This eerie glow is one of the most visually compelling demonstrations of relativistic effects in a setting accessible to direct observation. In particle physics experiments, large volumes of water or ice instrumented with photomultiplier tubes serve as Cherenkov detectors for high-energy neutrinos and cosmic ray secondaries. The Ice Cube Neutrino Observatory beneath the South Pole uses a cubic kilometer of Antarctic ice as Cherenkov medium, detecting the blue flashes of light emitted by particles produced when cosmic neutrinos interact in the ice. The Ice Cube has detected neutrinos of astrophysical origin at energies up to the petaelectronvolt scale, demonstrating the power of Cherenkov detection for high-energy particle astrophysics. The threshold behavior of Cherenkov radiation, the minimum speed a particle must have to produce it in any given medium, provides a useful diagnostic tool in particle physics. At threshold, the Cherenkov cone is very narrow and emission is directed mostly forward, increasing the solid angle as the particle speed increases. A particle that is just barely above threshold in water, but below it in a less dense medium provides a way to distinguish particles with different speeds at the same momentum, which is equivalent to distinguishing different masses. Ring imaging Cherenkov detectors exploit this by measuring the radius of the ring of Cherenkov light produced in a detector volume, with the radius corresponding directly to the velocity and therefore providing a mass determination when combined with a momentum measurement. The atmospheric Cherenkov technique used for very high-energy gamma-ray astronomy operates on a related principle. When a gamma-ray photon with energy in the range of hundreds of gigaelectronvolts enters Earth's atmosphere, it initiates an electromagnetic cascade, producing a shower of electrons and positrons traveling near C in air. These secondary particles move faster than the speed of light in air, roughly 0.99997 c, and emit Cherenkov radiation at a very narrow angle, about 1.3 degrees for these energies. The shower of Cherenkov photons reaches the ground in a brief flash lasting a few nanoseconds, distributed over a pool roughly 200 meters in diameter. Arrays of large aperture mirrors with sensitive cameras, called imaging atmospheric Cherenkov telescopes, image the shower and reconstruct the direction and energy of the original gamma ray to within 1/10 of a degree and 10% in energy, respectively. The crucial comparison that Cherenkov radiation illustrates is between the local speed of light in a medium and the universal maximum speed c in vacuum. The medium sets a local light speed, and particles can exceed this local speed without violating the universal limit. The universal limit and the local speed of light are two different things, a distinction that matters for understanding what the light barrier actually prohibits. No other phenomenon in physics has been more systematically misrepresented in popular accounts as faster-than-light influence than quantum entanglement, and the misrepresentation persists despite the fact that physicists who have studied the phenomenon carefully have understood for decades precisely why entanglement cannot be used to send information faster than light. Getting the picture correct requires understanding both why the correlations in entangled systems are genuinely non-classical and why non-classical correlations do not imply faster-than-light communication. Two particles are quantum mechanically entangled when their joint quantum state cannot be written as a product of individual states for each particle separately. The particles are in a superposition of correlated outcomes, and when a measurement is performed on one particle, the quantum state appears to update instantaneously regardless of the distance to the other particle. The measurement outcome on one particle is correlated with the subsequent measurement outcome on the other particle in ways that cannot be explained by any pre-existing properties the particles carried with them when they separated. A conclusion established rigorously by John Bell's 1964 theorem and confirmed by increasingly precise experiments beginning with John Clauser's work in the 1970s and culminating in loophole-free experiments in 2015. The correlations are real and are not explained by any classical hidden variable theory. Something genuinely non-local is going on. But the crucial question for faster-than-light communication is whether the correlations can be used to transmit information from one particle's location to the other faster than a conventional signal could travel. The answer is definitively no, and the reason is built into the structure of quantum mechanics. When you measure your entangled particle, you obtain a random outcome. The probability distribution of outcomes is determined by the quantum state, but which specific outcome you get on any given measurement is random and is not under your control. Your distant partner also obtains random outcomes. When you later compare your results through a conventional classical channel, you discover that the results are correlated in a way that violates Bell's inequalities. But neither of you, looking only at your own sequence of measurement results, can see any signal in them. Your results look like random noise. Your partner's results look like random noise. The correlation only becomes apparent when you bring the results together and compare them, which requires a classical channel limited to light speed. The impossibility of using entanglement for faster-than-light communication is formalized in the no-communication theorem, proven within the standard formalism of quantum mechanics. The theorem shows that the statistical distribution of measurement outcomes at one location cannot be affected by any local operation performed at a space-like separated location, regardless of whether the two locations share entangled particles. No measurement scheme, no choice of measurement basis, No sequence of operations on your entangled particle can alter the probability distribution seen by your distant partner. The entanglement is real. The non-locality of the correlations is real. The impossibility of using those correlations for faster-than-light signaling is equally real. The 2022 Nobel Prize in Physics, awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on quantum entanglement, brought renewed public attention to the phenomenon. The committee's language described quantum information as a new type of information and emphasized the implications for quantum computing and quantum cryptography. Absent from the Nobel announcement was any suggestion that entanglement enables faster-than-light communication, because the laureate's work, rather than finding such communication, was notable precisely for confirming the quantum mechanical predictions that prohibit it. The specific achievement that the Nobel Committee recognized was the loophole-free experimental demonstration that Bell's inequalities are violated by real, physical, entangled particles. This confirmation had important implications. It definitively ruled out the class of hidden variable theories that Einstein had hoped might restore determinism and locality to quantum mechanics. The correlations between entangled particles are real and are not explained by any pre-existing correlation the particles carry with them. But this reality is not faster-than-light signaling, because the correlations are only apparent after combining the random results from both measurement stations, which requires a classical channel. A thought experiment that clarifies why the correlations cannot be used for signaling is the following. Suppose you and a partner each have one particle of an entangled pair. You each measure your particle and record the results. Your sequence of results looks like random noise. Your partner's sequence also looks like random noise. Only when you compare your sequences using a telephone call or any other classical communication do you discover that the results are correlated in a way that violates Bell's inequalities. The correlation is only visible in the comparison, and comparison requires light-speed-limited classical communication. No information is transmitted faster than light by the entanglement itself. Electromagnetic waves in dispersive media present a subtler version of the apparent faster-than-light puzzle, one that requires carefully distinguishing between different quantities that all have the dimensions of velocity, but that represent fundamentally different physical things. A monochromatic wave of a single frequency has a definite wavelength and a definite speed at which its phase pattern, its peaks and troughs, propagates through space. This is the phase velocity, defined as the frequency divided by the wave number. In a dispersive medium, one in which the phase velocity depends on frequency, a pulse of radiation contains many frequency components traveling at different phase velocities. The overall shape of the pulse, its envelope, propagates at the group velocity, defined as the derivative of frequency with respect to wave number. In non-dispersive media, phase and group velocities are equal. In dispersive media, they can differ substantially. In anomalous dispersion media, where the refractive index decreases with increasing frequency over some range, the group velocity can exceed c. This sounds alarming. If the pulse envelope moves faster than c, is information being transmitted faster than light? The answer requires careful attention to what information means in this context. A group velocity faster than c does not mean that any new information is arriving at the detector faster than it would via a vacuum path. What is happening is that the medium's response to the wave's frequency components causes the pulse to be reshaped. The leading edge of the pulse, which entered the medium first, essentially predicts the behavior of the subsequent portions of the pulse and allows the medium to reconstruct the peak of the pulse before the vacuum path of the peak would have arrived. This is not faster than light communication because the peak of the outgoing pulse is not carrying new information. It is a consequence of the medium's known response to the known incoming waveform. If you encode a new signal, something that genuinely was not predictable from the prior portion of the incoming waveform, the leading edge of that new signal, the wavefront, still travels at most at c regardless of the medium. This was proven rigorously by Arnold Sommerfeld and Leon Brillouin in the early 20th century. The signal velocity, the speed of the wavefront carrying genuinely new information, is bounded by c in all media, regardless of what phase velocity or group velocity do. The 2000 Princeton experiment by Li Junwang and colleagues, which measured light pulses apparently exiting a cesium vapor cell before they had fully entered it, produced headlines suggesting Einstein's speed limit had been broken. The experiment was real and the results were accurately measured, but the interpretation required the distinction between group velocity and signal velocity. The cesium cell was operating in a region of anomalous dispersion, and the pulse's group velocity inside the cell was approximately 310 times c. But no information was transmitted faster than c, the leading edge of the pulse, and therefore any signal encoded in the pulse still propagated at c, and the early appearance of the pulse peak inside the cell was a consequence of the medium reshaping a predictable pulse rather than transmitting new information. The historical origin of the phase velocity versus group velocity distinction in the context of faster-than-light propagation goes back to the work of Arnold Sommerfeld in 1907, who was troubled by the apparent implication of earlier results that light pulses could travel faster than c in certain materials. Sommerfeld proved rigorously that the wave front of any pulse, the leading edge of the disturbance that represents the very first arrival of the signal, travels at most at c, regardless of the phase or group velocity in any medium. Leon Brillouin extended this work in 1914, identifying the different velocities relevant to wave propagation and showing that the signal velocity, the relevant quantity for information transfer, is always bounded by c. The physical reason the wave front is limited to c is straightforward. The wave front is the first arrival of any influence at a given location. Before the wave front arrives, no information about the source has reached that location. The wave front is therefore, by definition, the fastest information carrier in the signal. And in any causal theory of physics, the wave front cannot arrive before a light signal sent simultaneously with the original disturbance. The medium's effect on the wave is to reshape the interior of the signal, redistributing energy and phase among frequency components that have already arrived, but it cannot affect the wavefront because that is the first arrival. This argument is not just a derivation within classical electrodynamics. It is a general consequence of causality. Any causal response function, one in which the output at time t depends only on inputs at times earlier than t, has a Fourier transform that satisfies the Kramers-Kronig relations, which constrain the real and imaginary parts of the response function in ways that guarantee the wavefront propagates at most at c. The signal velocity limit is therefore a consequence of causality written in the language of linear response theory, connecting the faster-than-light communication question directly to the foundational principles of physics. Tachyons are hypothetical particles defined by the property that they would always travel faster than light, not by being accelerated past c from below, but by existing exclusively in the superluminal regime. The concept arises from a straightforward examination of what special relativity would require of particles in the three dynamical regimes defined by their relationship to c. For particles with positive real rest mass, the rest energy is mc squared. The particle can be made arbitrarily slow, and its speed in any reference frame is less than c. Increasing its energy increases its speed asymptotically towards c without reaching it. These are the particles we know: electrons, protons, neutrons, atoms, and the objects made of them. For massless particles, rest energy is zero, momentum is energy divided by c, and the particle travels at exactly c in all reference frames. These are photons and gravitons. For particles with imaginary rest mass, the mathematics of special relativity produces a different but internally consistent description. Imaginary rest mass means the square of the rest mass is negative. The energy of such a particle can still be real and positive for superluminal speeds, because the imaginary factors arising from the imaginary mass and the imaginary Lorentz factor for v greater than c combine to give real quantities. The energy of a tachyon decreases as its speed increases and approaches zero as speed approaches infinity. Adding energy to a tachyon slows it down. Removing energy speeds it up. The tachyon's minimum energy state, analogous to a massive particle at rest, is at infinite speed. This description is mathematically self-consistent within special relativity in the sense that no individual tachyon measurement in any reference frame violates the theory's equations. The problems arise when you consider what tachyons could do if they existed. Because they travel faster than light, there exist reference frames in which a tachyon appears to travel backward in time. If tachyons can be produced and detected at specific times by experimenters, then a pair of experimenters using tachyon communicators and moving at suitable velocities relative to each other could in principle send messages into their own past, creating the classic causal paradoxes associated with time travel. The status of tachyons in modern physics is interesting. No particle with negative mass squared has been found, despite extensive searches. The word tachyonic appears frequently in theoretical physics, but usually in a different technical sense. A tachyonic field is one in which the potential energy has a local maximum at some field value rather than a minimum, indicating an unstable equilibrium. The Higgs field in the standard model of particle physics was tachyonic at the origin of field space before electroweak symmetry breaking, which drove the field to settle into a lower energy minimum and give masses to the W and Z bosons and to fermions. This tachyonic instability of the Higgs field does not produce particles moving faster than light. It describes the vacuum structure of the theory. The causal structure of a tachyon's world line reveals the deepest problem with tachyons. In Minkowski spacetime, each event has a future light cone, the set of all events that can be causally influenced by that event, and a past light cone, the set of all events that can have causally influenced it. Events outside the light cones, in the space-like region, cannot be causally connected to the event through any subliminal influence. The tachyon, traveling faster than light, has a world line that lies in the space-like region of the light cone structure. In different inertial reference frames, different observers disagree about whether the tachyon is moving forward or backward in time. This disagreement is the reinterpretation principle, also called the switching principle, proposed by Alexei Bilaniuk and E.C. George Sudarshan in 1962. They argue that the ambiguity in whether a tachyon is moving forward or backward in time could be resolved by reinterpreting a backward-in-time tachyon as a forward-in-time tachyon with opposite sign of energy and momentum. If tachyons come in particle and antiparticle versions, the reinterpretation principle can consistently assign each tachyon to a specific future-directed world line. However, the ability to construct causal loops using tachyons, as the Alice-Bob time travel argument shows, persists even with the reinterpretation principle because it depends on choosing which reference frame to use for each transmission. The most recent comprehensive search for free tachyons has come from the Karlsruhe tritium neutrino experiment, COTRN, which measures the endpoint spectrum of tritium beta decay to determine the neutrino mass with extreme precision. If neutrinos had imaginary mass squared, their mass squared would appear as a negative number in the measurement, and the spectrum would show a characteristic distortion. COTRN's measurements, published in 2022, give a neutrino mass squared of 0.26 plus or minus 0.34 electron volts squared, consistent with zero and with small positive values, completely inconsistent with tachyonic neutrino mass. In 1994, the Mexican physicist Miguel Alcubierre published a solution to Einstein's field equations of general relativity that described a mechanism for achieving apparent faster-than-light travel without any object locally exceeding c. The mechanism was elegant and surprising, and it sparked a serious scientific conversation about whether general relativity contains the seeds of its own circumvention of the speed limit it nominally enforces. The idea begins with the observation that the restriction to speeds below c in special relativity applies to the motion of objects relative to local spacetime. It does not restrict how fast spacetime itself can move, expand, contract, or deform. The expansion of the universe already demonstrates this. Distant galaxies recede from us faster than light not by moving through space but by riding space as it expands. The Alcubierre metric takes this observation and applies it locally. What if you could create a region of spacetime that contracted ahead of a spacecraft and expanded behind it, effectively surfing a spacetime wave? In the Alcubierre solution, the spacecraft sits inside a flat, undistorted bubble of spacetime. This bubble is surrounded by a specific distribution of exotic matter that curves spacetime in precisely the required way, contracting ahead of the bubble and expanding behind it. The bubble moves through spacetime faster than c is measured by distant observers, but the spacecraft inside the bubble is locally stationary relative to the bubble's interior spacetime. At every point, the local speed of light is c, and no local observer measures anything exceeding c. Yet the spacecraft moves from one point to another faster than a photon would travel through the same flat space. The spacecraft's occupants would experience no acceleration during this travel. They float freely inside the flat space-time bubble, in a state of free fall. They would age normally during the transit, and the trip time as measured by their clocks would be the same as the coordinate time measured by distant observers. Unlike the relativistic time dilation that affects near-sea travel with conventional propulsion, the Alcubierre drive produces no time dilation relative to the external universe. The solution is mathematically valid. It satisfies Einstein's equations for appropriate distribution of the stress-energy tensor. This is what makes it scientifically interesting rather than merely science-fictional. The equations of general relativity permit it in the mathematical sense of being a solution to those equations. The question of whether it can actually be realized requires examining what the required stress-energy tensor looks like physically, and this is where the difficulties begin. The 1994 Alcubierre paper opened a productive direction in general relativistic studies of exotic spacetime geometries and the conditions under which they can arise. Following the Alcubierre paper, several authors extended and modified the metric to explore different bubble shapes, different velocity profiles of the bubble, and different distributions of the exotic matter. Van den Broek in 1999 proposed a modification in which the interior of the bubble was topologically enlarged to be much bigger on the inside than the outside, reducing the total exotic matter required by many orders of magnitude. This modification reduces the exotic matter requirement, but does not eliminate the need for negative energy density or resolve the fundamental quantum mechanical instability problems. Nat Fenning and Larry Ford examined the Alcubierre metric from the perspective of quantum inequality constraints in 1997, finding that the exotic matter requirements are not merely large but violate the quantum inequalities that constrain how much negative energy can exist in any region. Their analysis show that the ratio of the required negative energy to the positive kinetic energy of moving the bubble scales unfavorably with the thickness of the bubble wall, suggesting that no practical modification of the bubble geometry can satisfy the quantum constraints. Harold Johnson and collaborators at NASA's Advanced Propulsion Research Group conducted a series of studies in the 2010s that attempted to find modified versions of the Alcubierre metric that might be more physically realizable. Their work, conducted at the EagleWorks laboratory at Johnson Space Center, explored modified bubble geometries and attempted to detect any modification in the electromagnetic zero-point field that might serve as a laboratory signal of the metric. No positive results were obtained, and the theoretical underpinning of the approach was criticized by mainstream physicists. The Alcubierre metric requires a specific distribution of matter and energy to produce the required space-time curvature, and when that distribution is examined carefully, it turns out to require something that quantum mechanics appears to prohibit at any relevant scale: negative energy density in large amounts concentrated in macroscopic regions. Einstein's field equations relate the curvature of spacetime at every point to the energy and momentum content at that point. The curvature required by the Alcubierre metric, contracting ahead of the bubble and expanding behind it, corresponds to a pattern of energy density that must be negative in front of the bubble. Negative energy density means energy density below the vacuum value, which in classical physics is simply impossible, and in quantum physics is possible only in very limited and highly constrained ways. Ordinary matter, even exotic matter, has positive energy density. The vacuum itself has a well-defined energy, and quantum field theory allows fluctuations around this vacuum that can momentarily produce negative energy density in small regions, but these fluctuations are constrained by quantum inequalities that limit how much negative energy can exist in any region and for how long. The Casimir effect, in which two parallel conducting plates placed very close together experience an attractive force due to modified vacuum fluctuations between them, provides the best-known example of measurable negative energy density. The Casimir effect is real and has been measured with high precision, but the negative energy densities involved are many, many orders of magnitude smaller than what any macroscopic warp bubble would require. Harold White at NASA proposed modifications to the Alcubierre metric in 2011 that, he argued, could dramatically reduce the energy requirements. The original estimate placed the required negative energy at roughly the equivalent of the mass energy of Jupiter. White argued that by modifying the bubble geometry, specifically by making the bubble walls oscillate and by changing their shape, the requirement could be reduced to something more manageable. These proposals attracted significant media attention but have been criticized by other physicists for calculational errors, and the consensus in the theoretical physics community is that the modifications do not change the fundamental conclusion that macroscopic negative energy at the required scale is prohibited by quantum mechanics. The deeper issue is quantum stability. Even if negative energy could somehow be arranged in the required configuration, the quantum vacuum itself would be destabilized by the spacetime geometry of the warp bubble. Quantum field theory calculations propagating fields through the Alcubierre metric find that vacuum fluctuations diverge at the walls of the bubble, producing runaway energy densities that would destroy the bubble geometry before the bubble could form or sustain itself. This quantum instability appears to be a fundamental consequence of the geometry, rather than an engineering problem to be solved. The Alcubierre drive also faces a causality problem at a fundamental level. If the bubble moves faster than light, then the bubble walls are causally disconnected from the spacecraft interior. No signal from inside the bubble can reach the front wall because the front wall is moving away faster than any signal could travel. This means the occupants cannot control the bubble, cannot steer it, and cannot stop it using any mechanism inside the bubble. The bubble must be controlled entirely from outside, but the outside is causally disconnected from the interior during superluminal travel. Creating and controlling a warp bubble appears to require solving the faster-than-light problem before you can use the faster-than-light solution. Eric Lentz proposed in 2021 a different approach to warp drives that attracted attention because it appeared to avoid the negative energy requirement. Lentz described a class of general relativistic solutions called soliton solutions, which describes self-consistent deformations of spacetime that can move at any speed without requiring the occupant to exceed local c. The key claimed difference from the Alcubierre metric was that Lentz's solitons appear to require only positive energy density. The paper generated significant media coverage with headlines suggesting the negative energy problem had been solved. Subsequent analysis by multiple groups found that the Lentz solitons, while indeed not requiring negative energy density when described in the specific reference frame of the soliton itself, still require energy distributions that violate energy conditions when examined in other reference frames, and in particular require exotic energy arrangements that cannot be produced by any known physical process. The total energy required is also staggeringly large, roughly the mass energy of Jupiter, even in Lentz's most optimistic scenarios. The consensus among general relativists is that the Lentz solitons do not represent a genuine escape from the energy problems of warp drives. The most fundamental issue with warp drive physics may not be energy at all, but rather the measurement problem. How does an observer inside a warp bubble know where the bubble is going, and how do they stop? The bubble's interior is causally disconnected from its front wall during superluminal motion, meaning that signals from inside cannot reach the front. The bubble cannot be guided from within. And there is a radiation problem. As the bubble moves through space, it sweeps up quantum vacuum fluctuations and other background radiation, which build up on the front wall and would be intense enough to incinerate anything inside the bubble long before arriving anywhere interesting. A wormhole is a hypothetical tunnel through spacetime connecting two separate regions that are otherwise distant from each other. The concept entered serious theoretical physics in 1935 when Einstein and Rosen showed that the Schwarzschild solution to the field equations, which describes the spacetime geometry of a black hole, can be interpreted as containing a bridge connecting two separate flat spacetime regions. This Einstein-Rosen bridge is not traversable in the sense relevant to travel. The bridge collapses in zero proper time, and no object can pass through it, not even light. Traversable wormholes, the kind that could provide shortcuts for interstellar travel, were studied seriously by Kip Thorne and his collaborators in 1988 following a suggestion from Carl Sagan for his novel Contact. The Thorne-Morris wormhole is a solution to Einstein's field equations describing a stable tunnel with two mouths connected by a throat through which an observer could pass from one mouth to the other in a finite time, potentially much shorter than the time it would take to travel through normal space between the same 2 points. The requirements for maintaining such a wormhole are even more demanding than those for the Alcubierre drive. The wormhole throat must be threaded by exotic matter with negative energy density that provides the repulsive gravitational effect needed to hold the throat open against the tendency for gravitational attraction to collapse it. The scale of the negative energy required scales with the size of the throat. Smaller throats require more exotic matter per unit length. A throat large enough for a human to pass through would require negative energy far in excess of anything the Casimir effect or any known quantum phenomenon could provide. The quantum stability problem is equally severe. When quantum fields are propagated through the geometry of a traversable wormhole, vacuum fluctuations tend to diverge at the throat on sub-Planckian timescales, suggesting that any traversable wormhole would be destroyed by quantum effects before anything could pass through it. This result appears in multiple different approaches to the calculation and is widely accepted as suggesting that macroscopic traversable wormholes are quantum mechanically impossible, though a definitive proof requires a full theory of quantum gravity that does not yet exist. If traversable wormholes could exist, they would be equivalent to time machines as well as space tunnels. By moving one mouth of a wormhole at relativistic velocities, you can desynchronize the two ends in time due to relativistic time dilation. An object entering one mouth would exit the other at a different time, potentially in the past. This time travel connection is another manifestation of the general principle that any mechanism for faster-than-light travel can be converted into a mechanism for backward time travel through appropriate arrangement of reference frames. The classic paper by Morris and Thorne on traversable wormholes, published in the American Journal of Physics in 1988, laid out the requirements in detail and was notable for its explicit pedagogical intent. Thorne and his student Morris designed a paper partly to provide a worked example of using general relativity to analyze an exotic spacetime structure. The paper derives the constraints on the wormhole metric necessary to ensure that an observer passes through the throat with finite tidal forces and that the throat remains open long enough for transit. The exotic matter required to support the wormhole throat must have a stress-energy tensor that violates One of the many implications of an accelerating expansion is that an increasing fraction of the universe is being carried beyond the distance at which recession velocity equals c, never to be observed again. The relationship between distance and recession velocity in an expanding universe is described by Hubble's law. Recession velocity equals the Hubble constant times the distance. With the Hubble constant at approximately 70 kilometers per second per megaparsec, recession velocity equals c at a distance of roughly 14.4 billion light-years, a distance called the Hubble radius. All objects beyond the Hubble radius are currently receding from us faster than c. This does not mean we cannot see them. We can observe objects that are now much farther than the Hubble radius because the light we receive from them was emitted when those objects were closer to us and their recession velocity was less than c. The observable universe, bounded by the particle horizon at roughly 46 billion light-years, is larger than the Hubble radius. What is prohibited by the accelerating expansion is communication with currently super-Hubble radius regions in the future. Light we send toward objects beyond a certain distance will never catch them, because those objects are receding faster than the light can travel toward them, and the rate is accelerating. This boundary, the cosmic event horizon at roughly 16 billion light-years, defines the region with which we can ever exchange signals. Everything beyond it is permanently and irrevocably beyond our communicative reach, not as a practical matter of distance but as a fundamental consequence of the accelerating expansion geometry. The faster-than-light recession of distant galaxies is completely consistent with special relativity because special relativity is a local theory. It describes what happens in small enough regions of spacetime that the curvature of spacetime can be neglected and spacetime can be treated as flat. In such local regions, nothing moves faster than c. The recession velocities greater than c arise from integrating the local expansions of space over large distances, and they represent the rate of change of a distance measured in a specific cosmological coordinate system, not the local velocity of anything moving through its own local spacetime. The observational confirmation of the accelerating expansion came from measurements of the luminosity distances to Type Ia supernovae at redshift around 1, corresponding to when the universe was roughly half its current age. Type Ia supernovae are standardizable candles because they involve the thermonuclear detonation of white dwarf stars near the Chandrasekhar limit and have characteristic peak luminosities related to their light curve shape. By comparing the observed brightness of supernovae at various redshifts with their expected brightness based on redshift alone, both teams found that supernovae were systematically fainter than expected, meaning they were farther away than the expected distance for their redshift in a matter-dominated universe. The straightforward interpretation is that the expansion was slower in the past and has been accelerating, driven by the cosmological constant or some form of dark energy. The dark energy responsible for the accelerating expansion constitutes roughly 68% of the total energy content of the universe. Its nature is unknown. The simplest model, a positive cosmological constant, corresponds to a constant energy density of the vacuum, but its observed value is some 120 orders of magnitude smaller than what naive quantum field theory calculations predict for the vacuum energy. A discrepancy known as the cosmological constant problem and widely regarded as one of the deepest unsolved problems in theoretical physics. Alternative explanations involving dynamical scalar fields, modifications of general relativity at cosmological scales, and other mechanisms have been proposed and tested without definitive confirmation of any particular model. The practical implication for the question of what lies beyond the light barrier is that the accelerating expansion creates a new kind of fundamental horizon. Unlike the particle horizon that limits what we can see from the past, the event horizon limits what we can ever communicate with in the future. The region beyond the event horizon is forever outside the causal reach of any signal or traveler originating in our region of the universe. Cosmic inflation is the theoretical framework, developed initially by Alan Guth in 1980 and subsequently refined by many others, that proposes a period of exponential expansion in the very early universe lasting from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang. During inflation, the scale factor of the universe, the quantity that describes how distances between distant points evolve, grew by a factor of at least 10 to the 26th, and according to some models by far more than that. The expansion rate during inflation was not merely faster than c. It was faster than c by factors that make any comparison with human scale velocities meaningless. A region the size of a proton at the beginning of inflation was expanded to the scale of the currently observable universe, roughly 46 billion light-years, in approximately 10 to the minus 32 seconds. The rate of expansion vastly exceeded c, and the separation between nearby points in space increased faster than light could cross them. This sounds like a clear violation of the principle that nothing exceeds the speed of light, but it is exactly as consistent with special relativity as the current Hubble expansion. It is not objects moving through space at superluminal speeds, It is space itself expanding, carrying the objects within it apart. The distinction is precise and important. At every local point during inflation, the laws of physics, including the speed limit of c, applied normally. It is the global topology of the expanding spacetime, accumulated over the scale factor increase, that produced apparent recession velocities far exceeding c between distant points. Inflation's primary motivation was to solve three puzzles about the universe: the horizon problem, the flatness problem, and the magnetic monopole problem. The horizon problem is the most relevant here. The cosmic microwave background, the thermal radiation left over from the epoch of recombination when hydrogen atoms first formed, is extraordinarily uniform in temperature across the sky, to 1 part in 100,000. But in standard Big Bang cosmology without inflation, the regions of the sky in opposite directions should not have been in causal contact. Light from the beginning of the universe would not have had time to travel between them before recombination. Inflation solves this by proposing that the entire observable universe inflated from a single causally connected region that had time to thermalize before inflation began. The observational predictions of inflation that have been tested are remarkably successful. The spatial flatness of the universe, confirmed to high precision by measurements of the cosmic microwave background, is predicted by inflation. The nearly scale-invariant spectrum of density perturbations that served as seeds for galaxy formation is predicted by inflation. The statistics of the CMB temperature fluctuations, the acoustic oscillation peaks in the CMB power spectrum, are consistent with inflationary predictions. The search for primordial gravitational waves in the B-mode polarization of the CMB, which would be a smoking gun confirmation of inflation, continues with increasing sensitivity. The quantum mechanical generation of density perturbations during inflation provides a specific prediction that has been tested with remarkable precision. Inflation amplifies quantum fluctuations in the inflaton field to macroscopic scales, imprinting a nearly scale-invariant spectrum of density perturbations on the universe. These perturbations are the seeds from which all large-scale structure in the universe grew under the influence of gravity over the subsequent 13.8 billion years. The specific prediction is a power spectrum of density perturbations that is nearly, but not exactly scale-invariant, with a spectral index predicted to be slightly less than 1. The Planck satellite's precise measurements of the cosmic microwave background temperature fluctuations give a scalar spectral index of 0.9668 plus or minus 0.0037, consistent with inflation's prediction and inconsistent with a perfectly scale-invariant spectrum at high statistical significance. This is one of the most precise quantitative tests of any aspect of inflationary physics. Inflation also predicts a background of primordial gravitational waves, tensor perturbations analogous to the scalar density perturbations. These gravitational waves would leave a distinctive imprint on the polarization of the cosmic microwave background, producing B-mode polarization that cannot be produced by density fluctuations alone. The ratio of tensor to scalar perturbations, called the tensor-to-scalar ratio R, varies among different inflationary models and is currently constrained to be less than roughly 0.036 by joint analyses of CMB data from Planck and the BICEP/Keck array. Future CMB polarization experiments, including the Simons Observatory and CMB-S4, aim to detect primordial B-modes or push the constraint on R below 0.001, definitively testing a wide range of inflationary models. The relevance of inflation for the light barrier is that it demonstrates the universe has no objection to the expansion of space exceeding c when that expansion is a property of the geometry rather than motion through space. Whatever mechanism drove inflation, it operated without violating local speed limits while producing global expansion rates that dwarfed c by incomprehensible factors. The cosmic event horizon is perhaps the most philosophically provocative consequence of the accelerating expansion of the universe. It is not a physical boundary at a specific location in space, not a wall or a barrier that you would notice crossing. It is an informational horizon, a boundary defined by the future light cones of observers in an accelerating universe, beyond which no signal sent today will ever reach any observer in our region of the universe. The precise location of the event horizon depends on the rate of acceleration. With dark energy behaving as a cosmological constant, the universe is asymptotically approaching a de Sitter state in which the expansion rate is constant and the event horizon stabilizes at approximately 16 billion light-years from Earth. Objects currently within 16 billion light-years can receive signals we send today if they wait long enough. Objects currently beyond 16 billion light-years cannot receive our signals ever because the expansion will carry them away faster than our signals can travel. The shrinking of the observable universe over time is a consequence of this horizon. While the particle horizon, the boundary of what we can currently see from the past light cone, continues to grow as more time has passed since the Big Bang, the event horizon, the boundary of what we can ever communicate with in the future, does not grow and may shrink relative to the current distribution of galaxies. In the far future, all galaxies beyond the local group will be carried beyond the event horizon, and observers in the far future will see a universe containing only the galaxies of the local group, with the rest of the universe permanently invisible and inaccessible. The thermodynamics of the cosmic event horizon has a deep analog with black hole thermodynamics. Black holes have horizons with associated temperatures and entropies. The Hawking temperature is inversely proportional to the black hole mass, and the entropy is proportional to the horizon area in Planck units. De Sitter space, the spacetime corresponding to a universe dominated by a positive cosmological constant, has an analogous temperature proportional to the Hubble constant and an analogous entropy proportional to the event horizon area. The temperature of the current cosmic event horizon is approximately 10 to the minus 30 Kelvin, vanishingly small, but in principle physically real. The finite entropy of the event horizon implies a finite maximum information content for the observable universe, with profound implications for its long-term thermodynamic future. The entropy of the de Sitter event horizon, proportional to its area in Planck units, provides a bound on the total information that can be encoded in the observable universe's future. With the current event horizon area corresponding to an entropy of roughly 10 to the 122, in Planck units, the number of distinguishable states of the observable universe is finite. This is a number inconceivably larger than the number of atoms in the observable universe, but finite nonetheless. The finiteness of this entropy has profound implications for the long-term evolution of the universe under the assumption that the cosmological constant remains constant. A system with finite entropy confined to a finite region must, by the ergodic hypothesis of statistical mechanics, eventually pass through every accessible microstate. Over an unimaginably long but finite time, every configuration of matter and energy within the de Sitter horizon would recur. This is a cosmological version of the Poincare recurrence theorem. Sufficiently rare but not infinitely rare fluctuations would reproduce any configuration, including planets, life, and eventually any observer in any state, arbitrarily many times in the infinite future. The practical consequence of the event horizon for human civilization is the isolation of the local group. Over the next roughly 2 to 3 billion years, the most distant galaxies in the current observable universe that are not gravitationally bound to the local group will cross the event horizon and become invisible, their redshift increasing asymptotically toward infinity as they are swept away by the accelerating expansion. In 100 billion years, the local group will be the entire visible universe for any observer within it, surrounded by an apparently empty cosmos with no evidence in the CMB or in any other observations that other galaxies had ever existed. The connection between faster-than-light travel or communication and backward time travel is not a metaphor or an analogy. It is an exact mathematical equivalence derivable from the Lorentz transformation that relates space and time measurements in different inertial reference frames. Understanding the derivation makes clear that causality and the light speed limit are not two separate principles that happen to be consistent with each other. They are two faces of the same physical reality. The argument can be constructed precisely. Suppose two observers, call them A and B, are at rest relative to each other and separated by a large distance L. Observer A sends a tachyon signal that travels at speed v, where v is greater than c, from A to B. The signal arrives at B at a time L divided by v after A sent it. Since v is greater than c, this arrival time is less than L over c, the time a light signal would take. Both A and B agree the signal arrived after it was sent. No paradox yet. Now introduce a third observer, C, moving at velocity u relative to A and B in the direction from A to B, where u is a relativistic speed less than c. In C's reference frame, the departure and arrival of the tachyon signal are related by the Lorentz transformation. For sufficiently large tachyon speed v and sufficiently large u, the Lorentz transformed coordinates of the arrival event can be earlier in C's time coordinate than the departure event. C sees the signal arrive at B before it left A. Now B sends a tachyon reply to A using the same technology, traveling at speed v in B's frame. In C's frame, this reply signal also travels backward in time. The combined effect is that A can receive B's reply before A sent the original message. A has received information from the future. The time travel conclusion follows inevitably from the combination of superluminal signaling and the Lorentz transformation. Any theory that allows faster-than-light signals and respects the Lorentz transformation allows time travel. Any theory that forbids time travel and respects the Lorentz transformation must forbid faster-than-light signals. This is why the impossibility of faster-than-light communication is not an additional assumption in special relativity, but a consequence of its causal structure. The logical structure of the argument is important to understand precisely because various responses have been proposed to escape the conclusion. One response is to accept time travel but requires self-consistency, the Novikov self-consistency principle, which states that only self-consistent histories are physically realizable. Under this principle, an observer who receives a message from the future must send exactly the message consistent with having received that message, eliminating free choice but avoiding paradox. Another response is to invoke a many-worlds interpretation in which each apparently paradoxical time travel situation creates a new branch of the universal wave function in which no paradox occurs. Neither of these responses is entirely satisfactory. The Novikov principle eliminates agency in a way that seems physically questionable, and the many-worlds interpretation, while consistent, requires accepting a metaphysical framework that goes far beyond what physics requires. The cleanest response, and the one implicit in the structure of special relativity, is simply to reject faster-than-light signaling. If the universe's fundamental causal structure does not permit signaling faster than light, then the causal paradoxes never arise. This is the option that physics currently takes, and the extraordinary precision of the experimental tests of Lorentz invariance and of the no-communication theorem in quantum mechanics suggests that this is not merely a convenient choice but an accurate description of how nature actually works. The time travel connection also reveals something about the nature of the information that would be transmitted by a faster-than-light signal. The information received before it was sent would be information from the future, the reply to a question before the question was asked. Such information, if taken seriously, would allow prediction and therefore in principle elimination of the need for any decision-making. A consistent causal physics seems to require that the future not be accessible from the present, and the light barrier is the mechanism by which this inaccessibility is enforced. For most of the history of physics, the question of whether gravity propagates at a finite speed or instantaneously was either assumed or a matter of theoretical speculation with limited observational tests. Newton's theory of gravity, which served physics so well for 2 centuries, is a theory of instantaneous action at a distance. In Newtonian gravity, moving a mass instantaneously changes the gravitational field everywhere in the universe simultaneously. General relativity predicts that gravitational influences propagate at c, carried by gravitational waves that travel at the speed of light. The question was settled definitively on August 17, 2017, when the LIGO-Virgo gravitational wave network detected the merger of 2 neutron stars in a galaxy NGC 4993, approximately 130 million light-years away. The event, designated GW 170817, produced a gravitational wave signal consistent within spiral and merger of 2 neutron stars with total mass of roughly 2.74 solar masses. Approximately 1.7 seconds after the gravitational wave merger signal, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same sky location. Subsequent observations in optical, infrared, radio, and X-ray wavelengths by dozens of telescopes around the world confirmed the association. The 1.7-second delay between the gravitational wave and electromagnetic signals, after traveling 130 million light-years, constrains the speed of gravitational waves relative to the speed of light to a precision of 1 part in 10 to the 15th. This measurement rules out all alternative theories of gravity that predict different propagation speeds for gravitational and electromagnetic radiation across this enormous range. The gravitational waves and the photons traveled at the same speed to a precision exceeding that of any laboratory experiment across 500 million light-years of intergalactic space. This result has direct implications for theoretical physics. Several alternative theories of gravity, including some tensor vector scalar theories and some theories with extra dimensions, predicted differences between gravitational wave speed and light speed at levels now ruled out. The single observation of GW 170817 eliminated a large class of alternative theories overnight. More subtly, the result confirms that gravitational waves carry information, as photons do, at sea and not faster. Gravity is not a loophole in the speed limit. The observation of GW 170817 revealed much more than the speed of gravitational waves. The electromagnetic counterparts observed in the hours and days following the merger provided a comprehensive picture of the astrophysical event. The optical and infrared emission, called a kilonova, show the characteristic signatures of rapid neutron capture nucleosynthesis, the synthesis of heavy elements including gold, platinum, strontium, and other R-process elements in the neutron-rich ejecta of the merger. The kilonova's brightness evolution over days to weeks confirmed theoretical predictions for heavy element yields and established that neutron-star mergers are a major site of R-process nucleosynthesis in the universe. The gravitational wave signal itself, before the merger, shows the spiral of the two neutron stars as they lose energy to gravitational radiation, spiraling closer over millions of years before the final plunge. The final few seconds of inspiral, recorded by LIGO and Virgo with high signal-to-noise ratio, allowed measurement of the tidal deformability of the neutron stars, a quantity that depends on their internal structure, and the equation of state of nuclear matter at supernuclear density. This provided new constraints on the properties of nuclear matter at densities exceeding the nuclear saturation density, a regime inaccessible to any Earth laboratory. Subsequent detections in LIGO Virgo's third observing run and in the ongoing fourth run have added many more binary black hole mergers and neutron star merger candidates to the catalog. The growing sample allows population studies of compact object masses, spins, and merger rates, providing information about the formation channels of black holes and neutron stars in binary systems. Each detection also contributes to constraining fundamental physics, including the speed of gravity, Lorentz invariance, the graviton mass, and the compactness of neutron stars. The impossibility of faster-than-light communication has connections that extend beyond the specific equations of special relativity into the foundations of information theory and thermodynamics, suggesting that the light speed limit is not merely a relativistic rule but is connected to some of the deepest principles governing physical systems. Claude Shannon's information theory, developed in 1948, provides a mathematical framework for quantifying information and the capacity of communication channels. The fundamental limit of any communication channel is set by its bandwidth and its signal-to-noise ratio, but in any physical realization of a communication channel, the signals must be carried by some physical medium subject to the laws of physics. In our universe, those laws limit the speed at which physical carriers of information can propagate. The connection between information and thermodynamics runs through the concept of entropy. Maxwell's demon, the hypothetical entity proposed by James Clerk Maxwell in 1867 to challenge the second law of thermodynamics, was a creature that could observe individual molecules and selectively open a door between two chambers to sort hot molecules from cold, seemingly decreasing entropy without doing work. The resolution of the paradox, worked out by Leo Szilard in 1929 and refined by Rolf Landauer in 1961, is that the demon must measure the molecules to know which ones to let through, and erasing the memory of those measurements to keep the daemon functioning requires an energy expenditure at least equal to kTln2 per bit erased, where K is Boltzmann's constant and T is the temperature. Information has thermodynamic cost. The Bekenstein-Hawking entropy of a black hole connects information to spacetime geometry. Jacob Bekenstein showed in 1972 that the entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that the information content of a region of space is bounded by its surface area in Planck units. This holographic principle, developed further by Gerard T. Hooft and Leonard Susskind, has become one of the guiding ideas in quantum gravity. It implies that the information capacity of any region of space is finite and proportional to its boundary area. In this framework, the light speed limit appears not as an arbitrary restriction, but as a consequence of the finite information density of spacetime and the finite rate at which information can propagate. The Planck area sets the minimum pixel size of spacetime, and the maximum rate of information propagation is c, the rate at which one pixel of spacetime can influence its neighbor. The light barrier, from this perspective, is the universe's maximum clock speed, the rate at which one bit of reality can update the next. The connection between information and geometry in the holographic principle suggests a picture in which the light speed limit emerges from the way information is encoded in spacetime. If the information content of any region is proportional to its boundary area, and if that information is processed locally at the rate set by the quantum of action and the local energy, then the maximum rate at which information can propagate between neighboring regions is set by the geometry of spacetime and the Planck scale. The speed c emerges in this picture as the rate at which one Planck area pixel of spacetime can update its neighboring pixel. This holographic perspective on c is speculative and goes beyond what current physics has firmly established, but connects naturally to several active research programs. In tensor network descriptions of holographic spacetimes, the entanglement structure of the boundary theory encodes the geometry of the bulk spacetime, including the light cones that determine what can influence what. Modifying the entanglement structure changes the geometry and changes the effective causal structure. This suggests that spacetime geometry, and with it the speed of light, may not be fundamental, but may emerge from the entanglement structure of an underlying quantum theory. The firewall paradox, proposed by Almhiri, Merolf, Polchinski, and Sully in 2012, illuminated a tension between information conservation, the equivalence principle of general relativity, and the monogamy of quantum entanglement in the context of black hole physics. The paradox suggests that at least one of these three well-established principles must be wrong, or that they must be reconciled in a way that requires new physics. The ongoing debate around the firewall paradox has driven significant advances in understanding the relationship between entanglement, geometry, and causality in quantum gravity, and its resolution will likely have implications for the deep structure of the speed limit. Having examined what physics says about the light barrier with considerable care and precision, it is appropriate to address directly whether the underlying theory could be wrong. The honest answer is that special relativity has been tested with extraordinary precision across an enormous range of energies, distances, and physical systems, and no deviation from its predictions has been confirmed. But honesty also requires acknowledging that no physical theory has ever been proven correct at all scales and in all conditions, and special relativity may be an approximation to a deeper theory in some regime we have not yet probed. The specific ways in which Lorentz invariance, the symmetry underlying the constancy of c, could be violated at high energies have been systematically categorized in the Standard Model extension developed by Alan Kostelecki and collaborators. This framework parameterizes all possible terms that could be added to the Standard Model to produce Lorentz invariance violation at various levels and in various particle sectors, providing a systematic language for testing the principle experimentally. The constraints on Lorentz invariance violation are extraordinary. In the photon sector, measurements of the polarization of gamma rays from distant gamma ray bursts, combined with the known travel distance of billions of light-years, constrain any speed difference between different photon energies to less than 10 to the minus 22 in fractional terms. Any photon speed difference would rotate the polarization plane of light from a distant source by an amount proportional to the product of the difference and the distance traveled. Billions of light-years of travel time multiply any tiny effect to something measurable. No such rotation has been detected. The neutrino sector, following the announcement in 2011 by the Opera experiment at the Gran Sasso laboratory that neutrinos appeared to travel 60 nanoseconds faster than light from Sur to Gran Sasso, illustrates both the importance of testing the limit and the importance of experimental care. The anomalous result was eventually traced to two instrumental errors: a faulty fiber optic cable in the GPS timing system and an incorrectly functioning electronic oscillator. When these were corrected, the neutrino speed was consistent with c to the precision of the measurement. The episode was a reminder that extraordinary claims require extraordinary validation, and that systematic errors in precision experiments can masquerade as physics. If Lorentz invariance is violated at energies above the Planck scale, roughly 10 to the 28th electron volts, the effects would be undetectable with any instrument built from ordinary matter, because the matter itself would be described by physics modified at that scale. Whether quantum gravity theories predict Lorentz invariance violation at the Planck scale is an active research question. Some versions of loop quantum gravity predict it, while most string theory scenarios predict it is preserved. Current observations do not yet probe Planck scale physics, but the gap between current accelerator energies and the Planck scale is only about 15 orders of magnitude, and astrophysical observations of the highest energy cosmic rays, near 10 to the 20 electron volts, probe nearly 7 orders of magnitude above current accelerator energies. The most precise tests of Lorentz invariance in the photon sector exploit the enormous distances over which high-energy photons from astrophysical sources travel. If different photon energies traveled at even slightly different speeds, the accumulated time difference over billions of light-years of travel would be detectable. Observations of gamma-ray bursts, which emit photons over a broad range of energies simultaneously, have been used to constrain the energy dependence of photon speed. The Fermi Gamma-Ray Space Telescope observation of GRB 090510 in 2009 detected high-energy photons up to 31 gigaelectronvolts from a burst at redshift 0.9, corresponding to a look-back distance of roughly 7 billion light-years. The arrival time difference between the highest and lowest energy photons constrained the energy-dependent speed difference to less than 1 part in 10 to the 22 of c. These astrophysical constraints are complementary to laboratory tests and to constraints from the gravitational wave observations. Laboratory tests, including measurements with rotating torsion balances, atomic interferometers, and precision spectroscopy of ions and atoms, probe different combinations of the Lorentz violating coefficients in the standard model extension and achieve sensitivities in some sectors that exceed astrophysical observations. The combined constraint picture, covering many different sectors of the standard model extension, leaves essentially no room for Lorentz invariance violation at energies below the Planck scale. Any violation that exists must be extraordinarily small. Whether there is any motivated theoretical scenario that will produce Lorentz invariance violation at levels just below current sensitivity, but above zero, is an interesting theoretical question. String theory, the leading candidate for quantum gravity theory, generally predicts Lorentz invariance to be preserved exactly or to be violated at the Planck scale through highly suppressed operators whose effects at accessible energies would be undetectably tiny. Loop quantum gravity contains scenarios where Lorentz invariance is violated at the Planck scale with effect scaling is the square of the energy divided by the Planck scale, which for current measurements gives predictions far below current sensitivity. The theoretical landscape contains no strongly motivated prediction for a detectable violation, but the experimental search continues. The investigation of what lies beyond the light barrier is ultimately an investigation into the structure of reality at its most fundamental. The speed of light is not a coincidence, not an accident of the particular way electromagnetic phenomena happen to work, and not a practical speed record waiting to be beaten. It is the conversion factor between space and time in the geometry of the four-dimensional universe we inhabit, the parameter that defines which events can causally influence which other events, the rate at which the universe allows one part of itself to communicate with another. The phenomena that appear to circumvent the barrier, the expanding universe, cosmic inflation, geometric features like moving spots and intersection points, the phase velocity of waves and anomalous dispersion media, are genuinely interesting and are not illusions. They reveal that c is a limit on specific things: the motion of massive objects through space, the propagation of information, the transmission of causal influence, and not a limit on everything that can be described with a velocity. Understanding precisely what the barrier applies to and what it does not is one of the most productive exercises the subject offers. The proposals for genuine circumvention, warp drives, and traversable wormholes are also genuinely interesting, not because they are likely to be realized, but because they expose the architecture of the theory. They require negative energy density in macroscopic amounts, and the quantum mechanical prohibition on this, more fundamental than the energy calculations, suggests that the same quantum mechanics that make space a quantum foam of the Planck scale also enforces the light barrier at every scale above it. The barrier is not enforced merely by the classical theory, but by the quantum vacuum that underlies it. What does lie beyond the light barrier in an existential sense, the region of space-time that is permanently and irrevocably causally disconnected from here and now, is more universe, governed by the same physics, containing the same kind of structures, but permanently inaccessible to any signal or traveler originating in our location. The cosmic event horizon seals this region not with a physical wall, but with a causal geometry. The accelerating expansion of space forever outruns any signal we could send. And yet the question itself, what lies beyond the light barrier, continues to be productive precisely because it refuses to be fully satisfied by the current answers. The question probes the edges of special relativity, asking where its domain of validity ends. It probes quantum gravity, asking what modifications to space-time structure might emerge at the Planck scale. It probes cosmology, asking what lies beyond the observable universe both spatially and causally. It is a question that has driven some of the most significant advances in theoretical physics over the past century and seems likely to continue doing so. The universe has built its speed limit into the deepest layer of its structure, and the evidence for it is everywhere from atomic clocks on aircraft to gravitational waves from merging neutron stars. The evidence for new physics that might revise the picture is nowhere, yet. The appropriate response to this situation is not resignation but precision, understanding exactly where the evidence is, exactly what the current theory requires, exactly what form any extension of it would need to take, and maintaining the experimental sensitivity to detect any departure, however subtle, from the picture that is held for more than a century. What lies beyond the light barrier may be exactly what the theory predicts. Or it may be something that the next generation of observations will reveal in a form that no one has yet imagined. The history of physics provides both caution and encouragement for those hoping that future discoveries will change the picture. The caution is that the light barrier has been tested with extraordinary precision across an extraordinary range of energies and conditions, and every single test has confirmed it. The encouragement is that physics has repeatedly discovered that its most confident theoretical frameworks were excellent approximations to a deeper reality rather than final descriptions of it. Newtonian mechanics was not wrong in the sense of being contradicted by the observations available to Newton. It was incomplete in a way that only became apparent when new phenomena were discovered. Special relativity itself is an excellent approximation to general relativity in the limit of flat spacetime and weak gravitational fields. Whether the light barrier is one of the exact truths of a deeper theory or an excellent approximation to a more nuanced reality is the crucial unknown. The evidence favors the former. Lorentz invariance has survived every experimental test in a way that suggests it is exact rather than approximate. But exact theories do not emerge from approximate predecessors in physics. They emerge from experiments that reveal the regime where the approximation breaks down. No such experiment has yet been performed, not because the experimenters lack ingenuity, but because the regime where any deviation from special relativity is expected is at the Planck scale, 15 orders of magnitude above the highest energies achievable at current accelerators. The question that motivates the continued investigation of what lies beyond the light barrier is ultimately the same question that motivated the investigations that produced the discovery of the speed barrier in the first place. The desire to understand the universe as it actually is, without the comfortable scaffolding of intuition shaped by the limited scale of human experience. The universe has surprised physicists before and will surprise them again. The light barrier, with its extraordinarily precise experimental confirmation and its deep embedding in the structure of causality and information represents the current state of that understanding. What lies beyond it, in the physical sense of what new discoveries await, is the unwritten future of physics.